The final section of the course. So by now, we should know that one of the first things we want to do when we have a theorem like the divergence theorem is to practice verifying it. So let's take a look here. Let's say we want to verify the divergence theorem for f is the vector field y, yz, z squared, and the region D is a cylinder. Let me draw the picture here. Z runs from, let me draw all of the axes there. Z runs from 0 to 5, and it's x squared plus y squared is less than or equal to 4. So it's a cylinder of radius 2 here. And we're going from z is equal to 5, z is equal to 0. Okay, so in order to evaluate the divergence theorem here, I shouldn't say evaluate, I should say verify the divergence theorem. So, once again, it's going to be the double integral over s of f dot n. The sigma is going to equal the triple integral over d of the divergence of f dv. Once again, this is the divergence theorem. So on the right here, this will be a triple integral that we'll evaluate in cylindrical coordinates. It's a cylinder, so cylindrical coordinates makes the most sense here. On the left here, it's going to be surface integrals, and there's going to be 3 separate parts of the surface here. So one part is going to be the base of the cylinder. Remember, we are assuming here that our surface is closed. Doesn't have any boundaries, doesn't have any sharp edges to it. And so we need to include the bottom and the top of our cylinder. So 1 is the bottom, 1 is the top, and then finally the curved side to it. So we'll have to evaluate 3 separate vector surface integrals here. Okay, well, let's get to work. Let me call the side here S1, and then the top can be S2, the bottom can be S3, just to be able to talk about this. So this integral is equal to the integral over S1 of f dot n d sigma plus the integral over S2 of f dot n d sigma plus the integral over S3 of f dot n d sigma. Okay, we need to take these integrals one at a time. So for S1, we need a parametrization here of S1. So side of a cylinder, we should know that our parametrization R in terms of theta and z is going to be, so the radius here of the cylinder is 2, so 2 cosine theta, 2 sine theta, and z. And our normal vector, we just refer to what we did before. Our normal vector is 2 cosine theta, 2 sine theta, and 0. Okay, so then what do we need here? We need f of r of theta and z. So replace here y with 2 sine theta, y times z with 2 sine theta times z, 2z sine theta, and then z squared is just z squared. So this is our f of r of theta and z, f of r dot product n. So the dot product of this with this is going to be, let's see, this times this is 4 sine theta cosine theta. This times this is 4z sine squared theta. So the double integral over S1 f dot n d sigma, it's going to be, by the way, one thing I left out here is up here we didn't write down our bounds on theta and z. Of course, we're doing one full loop around. So theta runs from 0 to 2 pi. And from back here, we see z runs from 0 to 5. Okay, so what do we have here? This is going to equal the double integral over, so z is running from 0 to 5, theta is running from 0 to 2 pi, 4 sine theta cosine theta plus 4z sine squared theta d theta dz. I'm going to skip the computational details. You can check them for yourself. You get 50 pi here for your answer. Okay, that's S1. S2 is the top here. How do we parametrize the top? Well, we can just say here that this is the graph of the function, z is equal to 5. So for S2, this is z is equal to 5 for x squared plus y squared is less than or equal to 4. So our parametrization R2, we can parametrize this just with x and y. So we parametrize this just with x and y. Our parametrization is x, y, 5. And then our normal vector is just going to be 0, 0, 1 in this case, because we are pointing straight up. Remember, for the divergence theorem, it's an outward normal vector here, so we are pointing straight up. Okay, so we have R2, we have N. What else do we need here? We need F of R2 of X and Y. And so this is just going to be F, but replace Z with 5. So Y, 5Y, and 5 squared is 25. And then F of R2 dot product N. This dot product, this is 0 plus 0 plus 25. So what we are doing here is that our double integral over S2 of F dot N d sigma is the double integral of 25 dA over the region that's x squared plus y squared is less than or equal to 4. This is a circle of radius 2. This is a circle of radius 2. The area of the circle of radius 2 is going to be 4 pi. So when we integrate a constant over this, this is 25 times the area. And the area of that circle, as we just said, was 4 pi. 25 times 4 pi is 100 pi. Okay, so we've got, let's do our scorekeeping again here. This is 50 pi plus 100 pi. Now we need to do one more calculation for the left side of the divergence theorem. We need to integrate over this region right here, the bottom of our soup can. And so, what do we have? The double integral over S3 of F dot N d sigma. Here, the surface is going to be R3, I'll say R3 of xy. So this is, we can just parametrize this by x, y, and z is equal to 0. X, y, and 0. So f of R3 is going to equal, just replace z with 0, y times 0, 0, 0 squared is 0. So this is f of R3 here. The normal vector is, we need to make sure this is pointing outwards, so this is pointing straight down. And so our normal vector is 0, 0, negative 1. course, if you don't believe me, just crunch out things with, find the normal vector from scratch from R3 of x, y. But make sure that you have it pointing straight down. Okay, and what is f of R3 dot n? 0 times y plus 0 times 0 plus 0 times -1. That's just 0. So we're integrating over some region x squared plus y squared is less than or equal to 4. We're integrating 0, and we get 0. So what do we have here? 50 pi plus 100 pi plus 0. So the left side of our divergence theorem is 150 pi. Okay, so that is one calculation. Now we need to do the other calculation. We need the divergence here. So the divergence of f. So it's the x partial derivative of the first slot. That is 0. Plus the y partial derivative of the second slot here. That is z. Plus the z partial derivative of z squared. That's 2z. So the divergence here is 3z. Okay, so we have a triple integral then that we need to evaluate. Okay, what are the bounds here? We said we're going to do in cylindrical coordinates. Z runs from 0 to 5. And we're integrating 3z. We're switching here to cylindrical coordinates, so we need to throw in the factor of r. dz, dr, d theta. And here r is going to be, so the maximum radius here is 2. R runs from 0 to 2. Theta runs from 0 to 2 pi. So this is the integral that we need to evaluate here for the right side of the divergence theorem. I'll spare you the details so you can check it yourself. But again, you get 150 pi. And so this shows that the integral of f dot n over, the flux of f over the surface here, orient outwards, is equal to the triple integral of the divergence of f over the region inside of our cylinder. And so this plus this plus this, the sum of the three vector surface integrals, is equal to the triple integral here of the divergence over the cylinder.